Welcome back to Computer Science 1JC3. We're going to continue talking about the topic, what is functional programming? We mentioned that computers store and manipulate information. This information can be broken down into what we could call data, but we're going to call pieces of this information values. And there are various kinds of values that computers manipulate and store. There are Booleans. These are values that represent the truth values, true and false. There are machine integers that represent a finite set of small integers in a very effective, efficient way. There are floating point numbers that represent a finite set of rational numbers in scientific notation. There are strings, which are sequences of characters that you can use to represent words and sentences. There are tuples that represent sequences of values that are possibly different kinds. Lists, which are sequences of values of the same kind. And finally, there are functions that represent mathematical functions. And there are various ways that mathematical objects and data in general can be represented in programming languages, and this is one of the topics we will be discussing at the beginning of this term. So values are the information that computers, programs are going to store and manipulate. So let's talk now about how we refer to these values. The key idea is what we're going to call an expression. An expression is a syntactic entity that denotes a value. So what does that mean? A syntactic entity means it's something that has a syntax. This syntax is built up according to certain rules. Like in English, we have syntactic rules. These rules say what is a word, what is a noun and verb, what is a sentence, and so forth. So expressions are syntactic entities, and they have a meaning. They have something they represent that is a value. And we say that the expression denotes a value. The expression denotes its meaning, what it's supposed to mean, its value. So let's look at some examples here. The first is x times 2 quantity plus 7. If we think of x as having some value that's an integer, let's say 2, this would be 2 times 2 plus 7, so the value of the whole expression would be 11. If we look at the second example, this is the string ABC. So we're talking about a sequence of 3 characters, A, B, and C, put together. So it denotes that string. The third example is true, and we have this double ampersand. This stands for the logical operator and, so it's true and y. So if the value of y is true, if y denotes true, then this would be true, and so the value of the whole expression would be true. So these are some examples of expressions. The simplest expressions, which we'll call atomic expressions, you can't break them down any farther, are identifiers like x or like rotate horse. They're what people often would call, they represent constants or variables. And another kind of atomic expression are literals. So literals are called literals because the form of the atomic expression shows you the value. So here we have a literal, which is a 2, a period, and a 3. Its value is 2.3. Here we have a literal, which is double quote, CAT, double quote. Its literal value, it literally shows that its value is the string CAT. And finally, this literal, true, it literally tells you that its value is true. Now, compound expressions, we build up from other expressions, in particular from atomic expressions, by applying functions or operators. So here, we have ABS, which is the absolute value function applied to 10. So this ABS 10, that's an expression. Now we have 1 plus 2. Here we're applying the addition operator to 1 and 2, but we're able to, for convenience, be able to write the addition operator as in infix format. So it's between the 1 and the 2. So if we have an expression, it's useful to know what value the expression denotes. This is determined by evaluating the expression. So if we have expressions in a programming language and we want to know the value of the expression, the programming language implementation will usually let us find that value by evaluating the expression. Okay, so we have values, we have expressions. So here's a question about expressions. Which of the following is not a literal in Haskell? And we have false, we have 1 with a whole bunch of zeros after it. We have the secret is to reboot, exclamation mark in between double quotes, and we have X followed by 1887. So one of these is not a literal. And remember, a literal is an expression whose form literally tells you its value. So you can stop here, take a few minutes, think about the answer. Okay, now that you're back, we can go through each of these and see that false, it's a literal. The value of false is false. The value of this expression, which really represents a numeral, is the number represented by that numeral, which is some big number. I'd have to figure it out. I have to count how many zeros are here. The third thing is a literal because it denotes the string, particularly the string the secret is to reboot. And finally, the last one is not a literal. This expression is actually an identifier. It doesn't tell us in a literal way what its value is. Its value could be, as far as we know, almost anything. So this is the answer. Okay, so as I said, we have values, we have expressions that don't denote values. Now we have another kind of thing called types. These are data types, but we'll call them just types for short. Types are also syntactic entities, but they denote a collection of values, and it's a collection of values that have similar form. So it's not a mishmash of different kinds of values. It's values that have the same form. So here we see several examples in Haskell of different types. We have bool, which denotes the values true and false. Another way of saying it, bool denotes the Boolean values, the collection of Boolean values. Int denotes the set of machine integers. Remember, these are small integers. We're going to talk more about these later. Small integers that can be efficiently stored and manipulated. But there's only a finite number of them. Float denotes the set of floating point numbers. Integer denotes the set of integers. Integer, and by the way, it denotes the set of all integers, the full set of integers, including negative and positive integers as well as 0. Integer arrow integer denotes the set of all functions that take an integer as input and return an integer as output. So you may wonder, well, why do we have types? Why are they useful? Well, we have them because there's a very, very common kind of error in programming called a type error. This is an error when we apply an operator to a value, an expression, and the expression doesn't have the right kind of value. So if I applied addition to two values, but one of the values, let's say, wasn't a number, it was something else, let's say a truth value or a string, we would get a type error because addition can only be applied to numbers. So type errors are very common, and we'd like to be able to identify these type errors. So in Haskell, we can take an expression and we can type check it. And we can tell before we even evaluate it whether there are going to be any type errors. So we can fix the type errors before we actually evaluate the expression. Another way of saying it, we can identify these errors before we run the program. And even more importantly, these errors won't ever occur when the program is run because we won't allow the program to be run if there are type errors. Now you may wonder, well, how in Haskell do I find out the type of an expression? It's simple. I write down colon type, and then I write where the E here is. I just put the expression. And then the Haskell implementation will tell me what the type is. Now types are used extensively in computing and logic. They are used in mathematics, but they're used in a less formal, more disguised way. So to review a bit, we have values. This is what we're going to manipulate. We have expressions that denote these values, so we can refer to them and talk about them. And we have types, which denotes collections of values that have similar form. Okay, so here's a types question. Which type in Haskell contains infinitely many members? And you have 4 choices: bool, int, float, and integer. Now, to clarify a bit, there are types that contain infinitely many members in theory, because we could never store an infinite number of different values on a computer. We can only at most store a finite number of pieces of data. But we could develop our programming language, so in theory we could have a type that could include a member of an infinite set. So it could, as long as we had enough memory, it could include any particular member in that set. Okay, so there are types in Haskell that have infinitely many members. One of these types, bool, int, float, and integer, has an infinite number of members. Which is it? Well, I'll give you a moment. Think about it. Okay, now that you're back, could it be bool? Well, no. Bool is a type that has exactly 2 members, true and false. Is it int? No. Int is a type that denotes a set of machine integers, which is by definition a finite set of integers. And float denotes a set of rational numbers, which by definition is also finite. The reason these two are finite is because the members of each of these types is represented by a fixed number of bits. So let's say it's n bits. If it's n bits, then we can represent at most 2 to the n integers, or at most 2 to the n rational numbers. So that leaves D. D is a type integer. It's different from int because it represents the full set of all possible integers. Okay, so let's talk about functions a bit. This is probably going to be a review for most of you. You've probably figured out by now that functions are one of the most important values in mathematics and computing. The idea of a function is really one of the most powerful ideas in mathematics. And there's 2 ways of thinking about functions. You can think about them as a rule or as a value. And often we want to think about them both ways. So if we think about a function as a rule, we often write it down like this. We'd say f colon I arrow O, and the f is the name of the function. I is a set of inputs that the function can take. O is a set of outputs that the function can produce or give. So a function is a rule that takes an input and produces an output. And it produces, if you give it an input, it can produce at most 1 output, but it doesn't actually have to produce an output for every input. That's important. And so here's an example. This is a function f. It takes something from what's called blackboard Z and gives something from blackboard Q. Z, traditionally in mathematics, represents the set of integers, and Q here traditionally represents the set of the rational numbers or quotients. So this function takes an integer and produces a rational. It takes an integer and produces a rational. The rational it produces is the reciprocal of its input. Perfectly good function. It works in every case except when x is 0. When x is 0, we're going to get the reciprocal of 0, and 0 does not have a reciprocal. So it is, we say undefined then. In that case, the function does not produce an output. So that's what a function is as a rule. As a value, a function is a set. We can think of f as a set of ordered pairs where the first member of the ordered pair is the input and the second is the output. But it's not just any set of ordered pairs. It's a set of ordered pairs that satisfies this property. If I have x, y, and x, y prime in my set, then it must be the case that y equals y prime. This corresponds to the idea of a function as a rule, that as a rule, if it takes an input, it can only produce at most one output. So if we think of the first members of the pairs as input and the second members of the pairs as output, a function as a set must have this property. It must not associate more than one output with a particular input. Now functions have domains. The domains are the set of inputs on which the function is defined, and they have ranges. That's a set of outputs that can actually be achieved by the function. And there are certain properties, very important properties, called total, normal, total, surjective, injective, and bijective. So I'll quickly go over what these are. And so let's draw a little picture. I'm going to draw a little picture here. I'm going to have a box. And I have another box. These are meant to be sets. This is going to be the set of inputs. This is a set of outputs. And I'm going to have a function that's going to map inputs, outputs. So it's going to take a point here, and it's going to map it to a point here. Now the domain is a set of all inputs that actually get mapped to an output, and the range is going to be the set of all outputs on which some input actually gets mapped. So if we look at a point here, there's no input that every input, if we take any input here, it will not be mapped to that point because it's outside of R, the range. So that's a basic picture, and then we have these notions of total. What does total mean? Oops. Let's see if I can erase that. Over time, I'll get better at writing this way. So total, what does that mean? Total means that the domain equals the whole set of inputs. That means the function is defined in every input. So that's total. And then we have surjective. Let's try this again. Surjective. Maybe instead of this, I should just say this. Surjective means that the range is the entire set of outputs. That means the function, you can get to every output from some input. And then there's injective. Injective means that if I look at my function and I apply it to x, and I apply it also to, let's say, y. So I start with input x and get some value, and I get the same value input y. That means that x must equal y. In other words, if my function is injective, if I have 2 points here, and they this one goes here, and this one goes here. If it's injective, they can never be the same point. So that's injective. And then finally we have bijective. What's bijective? Bijective is total plus surjective plus injective. Now sometimes you may have heard that bijective is surjective plus injective. When people say that, they're assuming all functions are total. In computing, we do not assume all functions are total. Okay, so let's see, I think this, it's moved over a bit. Okay, so that's what a function is. And this is what are called N-ary functions, because these are functions that just take one input. We can have N-ary functions. They can take any number of inputs, any natural number of inputs. And so the way it works is it's pretty much the same. We can take n inputs, produce an output, and the rule is going to associate with those n inputs a particular output, at most one output, possibly no output at all. So they work exactly the same. The only thing a little bit confusing here is notice that n could be 0. What happens when we have n is 0? Well, that would be a function that takes no inputs, but it could produce an output. This is essentially the same as a constant. So it means you could think of something like 2 as a function. This would be a function that doesn't take any inputs, but always produces a value 2. So actually you could think of values themselves as functions, as zero-ary functions. So that's what a function is as a rule, N-ary function as a rule. If it's as a set, it's just going to be a subset of the Cartesian product of I1 through In and O. And if you know what the Cartesian product is, for instance, if I have A cross B cross C, what that really is a set of tuples A, B, and C. A tuple here is, in this particular case, is an ordered triple, and little a is in big A, little b is in big B, and little c is in big C. So that's what one of these Cartesian products are. A Cartesian product is a set of tuples. In this case, we have a Cartesian product of 3. So that is what an N-ary function is as a set. And again, we can define the domain and range in just the same way. Now, the interesting thing is, I'll point out something you probably may have already discovered, is that in Haskell, all functions are N-ary. In Haskell, we only have N-ary functions. So that begs the question, well, how are we going to represent N-ary functions if all functions are N-ary? Well, there's actually 2 ways we can do this, and Haskell supports both ways. The first is, let f here be a N-ary function, takes n inputs and produces output. I could think of this function as, instead of taking n different inputs, it takes one input. One input here. We can think of it as I is a member of that set. That input, what it is a tuple. So f only takes, so f prime, notice this is f here, this is f prime. They're not the same functions. But if I apply f to x1 through xn, that's the same as applying f prime to the tuple. Now you may say, this seems almost the same. Well, it is almost the same, but technically there's a difference. F has n inputs, F prime has one input, but it's an input that's complex because it's a tuple of n things. So that's an obvious way to turn an N-ary function into a unary function. But there's another way, and this is we can have a curried function. I told you we'd be talking about this, named after Haskell Curry. Here we have f is an N-ary function, and what we're going to do is we're going to represent this as a unary function by so-called currying it. Now this is going to take a while to sink in. This isn't probably going to be familiar to both of you, but it's fundamental for understanding Haskell and functional programming in general. So it's going to take a while, but you'll get it in time. So here we have a new function f prime. Notice it takes just one input, therefore it's unary. But notice what it gives back. It gives back a function. And what does that function do? That function, it takes another input. And that gives back another function. And then that function takes another input and gives back a function. In fact, we do this n times. So f now, when we apply it to n arguments, is the same as f double prime, where we apply it to the first argument, which is here, and then we get back a function. We apply that to the second argument, and we keep doing that till we end up applying it to the last argument. But these two functions are different, but they do the same thing. In the end, they do the same thing. They're going to give you the same value. Okay, so here's another question. So we have two functions, f and g. And what we know about f and g is that when I apply f to the tuple, the pair, the ordered pair, x, y, it's the same as applying g to x and then applying g to y. And we're thinking of x and y as being real numbers. If we look here, this is blackboard R. It's a normal symbol in mathematics for real numbers. So the question is, are f and g the same function? Actually, the way I put it, I gave a statement, was that f and g are the same function. Is this statement true or false? So I'm going to give you a moment to think about that, and you can decide whether the statement's true or the statement's false. Okay, now that you're back, let's go up here and look at this. These functions are always going to, in the end, give the same value. But they're not the same function, because f here, it takes a tuple of two real numbers. G here, it takes a real number, gives back a function that takes a real number. So they have the same results, they're different functions. So the answer here is B. Okay. We're going to stop right here. We've talked about what functions are. Now we're going to talk next about how functions are actually used and dealt with in Haskell. Okay, so thank you very much. See you next.